So, hi everyone. I'm Tom Talpey. I'm reporting here from Microsoft Central. Not really. I love the backgrounds that Zoom lets you put in. Thanks for inviting me back. I don't know how many sambaXPs I've been to, but it's been a bunch. So I'm really happy to be back. I'm really happy to see it continuing even with the current challenges. So my talk today is an SMB3 protocol update, the 2020 edition. I want to basically bring you up to date since last year, when we met last May, I believe it was. The update in the current 20H1 will be a major bit. There's only one real protocol feature to talk about, but it's got a lot of details. So I think we'll be interested in this development level. I want to give a view to the protocol changes coming and talk about some other related developments in the area of SMB and its protocol changes. All right, important. This presentation has been prepared with all appropriate social distancing. It's been quarantined, and I believe it is free of viral influence. Okay. It's really good to be presenting here. I'm really happy that we're still able to carry on our normal activities, albeit in a new way. The MS SMB2 document, our favorite document, was updated on March 4th, 2 months ago. Almost 3 months ago, huh? We published this 45 days prior to a release. We originally planned the release in April. It's moved to May. So we still published it back on March 4th. At the, quote, familiar URL, and of course the URL is a big mess. You can leave the GUID off. You can just, if you remember the beginning of it, ms-smb2. Alternatively, just do a Bing search. Bing deep indexes the Microsoft web pages, and so it gives you a pretty good view of all this stuff. We also have errata that are published regularly, and I highlighted the date of the most recent one, May 25th, just a few days ago, Monday. Memorial Day holiday in the US, actually, but it was published that day. There's a lot of interesting stuff in there, and I'm going to mention it and show it to you, so you don't have to go there. So the protocol changes. MS-SMB2. Currently, we're working on something called the Windows and Windows Server 20H1 release, first half of calendar year 20, aka Windows 10 version 2004. That's supposed to be year 2020, month 04. Here it is, almost the end of May. Windows Server was actually released yesterday. I am not sure. I have not looked to see if the Windows Client was released today, tomorrow, or whatever. But it will be released soon, any day now. It's been in preview for some time, so many of you have already seen it, I hope. The doc was updated March 4th, as I just mentioned. And today I want to also cover the 19H2, the previous fall release. My goal in doing that is to catch us up since sambaXP 2019. For those who didn't go to the Storage Developers Conference or who haven't seen it, I want to paint a year's picture of SMB. Fortunately, there's not a lot of news in the 19H2, but you'll see it. So here we are. This is 19H2, summer/fall 2019. 19H2 was released, I believe, in September, perhaps October of last year. And it was designated as a quality release overall. It had very few features across the board. It was largely geared towards stability and updates to components just to make sure that it was a high quality release. It's not that Windows quality had slipped, but it was perhaps at risk. There was a definite attempt to sort of tighten things up. And that was in preparation for changes that you're seeing today and in the future. And also just to make sure that things were stable. There's been a real doubling down on quality across Microsoft products. And the 19H2 release was intentionally held back. Features were intentionally held back in order to improve the quality. So the MS-SMB2 document is similarly changed, basically, it was only maintenance. There are no new features in SMB3, SMB2 appearing in the fall release. Just some bug fixes and a number of document fixes. Just a list. This is almost a complete list. The net name negotiate context we had documented as null terminated. It's not null terminated. Okay, there's a stop the presses moment, right? File IDs and their relationship to the objects in MSFSCC, the companion document, and how those file IDs are used for caching. That was that. There was a good bit of document structural cleanup, and a bunch of common text was merged. And there were some template fixes. The abstract data model was updated and reused a little bit. So for the most part, content did not change, just clarity in the document, echoing the quality task. I want to also mention that it was relatively quiet for TDIs. We didn't get a lot of bugs in the TDI space. There were a few, and some of them were interesting, but it was relatively quiet. And so the change going in was relatively small. Winter and spring, leading up to now, basically, between 2019 and 2020, there have been many more changes. Both these diff documents that I show in the little snippet at the top bullet are available on the web from the main download page. These are redlined PDFs. You can also get Word documents. You can see them in HTML. You can see them in lots of different ways. But the diffs are published via PDF. So 20H1, the upcoming release, the any day now release, contains new SMB3 changes. Primary among them, change compression and a new pattern V1 compression algorithm. I'm going to spend a good bit of time on this in a second, so I won't go into great detail here. We had a somewhat increased TDI level from our protocol partners, including Samba. Thank you extremely very much. And we also had TDIs coming from the Microsoft protocol validation testing. As you may know, anytime there's a so-called major change to the document and to the protocol, there is a offline protocol testing process by which the Microsoft Windows implementation and the document are both tested for accuracy. We get quite a few bugs from this. Sometimes a couple handfuls, sometimes more. And they tend to be clarity related because the test engineers actually read the document and attempt to implement the protocol changes based only on what's in the document. As well, when they test the Windows implementation, they discover little differences or little questions.
Tom, may I interrupt you for a second?
Yes, please.
The sound is fading in and out for about 10 seconds. We can hear you very clear if it's there, but if you're out, we can't hear you at all. Can you maybe change the audio settings to advanced and there is a noise gate? Maybe it's something in there.
Perhaps I can. One other possibility is that I have a digital mic which is directly in front of my face. I might be occasionally turning my head. Does that cause it to fade? Is it clearer when I have my voice pointed straight ahead like this?
No.
No difference? Okay. My microphone level. Where is my microphone level control panel? No, that's not going to help. Oh dear. One moment. No, unfortunately, I'm not seeing a gain control. My microphone meter is advancing normally.
Maybe it helps if you go just a little bit closer to the microphone.
I will attempt that. The microphone contains my video as well, so I might look a little different.
Okay.
Okay, well, I apologize. I believe I tested it before, but perhaps not in quite the same settings. I will attempt to make sure I stay clear. Please interrupt me if it's not. Okay, primary change to SMB3 in 20H1 is chained compression with a new pattern V1 algorithm. The pattern V1 algorithm will be the subject of a bunch of slides just coming up. The somewhat increased TDI level that I believe I was just talking about, I'm sorry, I'm rethinking here. We had a number of TDIs from the testing process, and they were largely integrated either slightly before or slightly after we released this March 4th document. Additionally, document maintenance is always occurring in the background from partner TDIs, from general things that we notice as we're fixing other TDIs. The only one that I'll really call out is there's some op-lock and leasing additional new discussion. We discovered that we had omitted a few important things, kind of left them to the reader's imagination. So we put them in a little more explicitly, and I hope we've improved that quality in terms of op-lock callbacks. Recent errata, as I mentioned, published most recently on May 25th, although we had a couple of cycles back in earlier May and even in April. There were some significant clarifications for the pattern V1 and chain compression discussion. I regret to say that some of them there were some significant omissions in there, and the testing and the re-review encountered quite a few of them. So there have been some big changes. I'll show them to you in a little bit. We also added some text on multi-channel processing, which was perhaps lacking. Most of it was there, but some of the Windows policies were missing. Some session scavenger processing and client GUID handling, and reconnection, lease cleanup, encryption fixes here, there, and everywhere. This URL at the bottom is the URL to the direct MS SMB2 errata. You can just go to the MS Win errata page and scroll down to find the SMB2 page. So diving into the new protocol features. The big feature is pattern V1 and chained compression. That's really the list at the moment of new features. Pattern V1 compression algorithm and the ability to do chained compression. So we'll be discussing both of those today. But I want to stress that they don't replace the existing compression processing. All the existing processing and policies remain. This is sort of like an additional compression policy and compression algorithm that will be applied. Again, there's no dialect change. We're still on 3.1.1. As I said last year, we don't foresee a dialect bump. With the addition of negotiate contexts and tree connect contexts, it's really not necessary to bump the basic dialect to change the protocol. We're able to extend the protocol in a compatible, forward-compatible way using these new negotiate and tree connect contexts. Here, we only change the negotiate context. Compression. We have modified the negotiate context SMB2 compression capabilities. That is a new new flags in the negotiate context. We've added a new bit called compression capabilities flag chain. We've added a new algorithm pattern V1. That pattern is defined in MSSMB2 itself. It's not in a companion document FCA like the other one. And you'll see why. It's very specific and very simple. They're defined in two sections, these two new sections. The new protocol modifies the SMB compression payload header. We've made the original payload size optional for the original compression algorithm. Specific to the original compression algorithms. It's optional for the new algorithm. It's left out, in fact. We've added a chained flag. And then finally, we've added this new compression pattern payload V1, and that is the actual compression payload that takes the chain compressed payload. There are no changes to the existing negotiation or algorithms. All those were covered in my talk last year, so you can see all the gory details of compression if you look back. A quick review, just to help. The client optionally negotiates compression by appending a negotiation context. The idea is 3. This is the context declaration. I highlighted the flags because we've added a flag. But basically, the server inspects the negotiate compression or the negotiate context coming in, swizzles it as it sees fit, as it supports the algorithms, and it replies. And so after a single exchange, the client and server have agreed on a set of compression algorithms. So we've added a flag to that set, and we've added an algorithm to that set. The compression transform is what happens as segments, as requests and responses are exchanged. Within an individual request or response, an eligible segment is replaced with a compression transform, basically a header, as an SMB2 transform header. And there were 3 algorithms defined. Now there are 4. There's an additional flag defined in the field. There's a slight change to the offset and length handling. We'll talk about in a second. Compression negotiation flags and algorithms. So this is the flag, capabilities flag chain. This is what's exchanged in the negotiation. And the new algorithm is called pattern V1. They're highlighted at the bottom of the list. It's a pattern scanning algorithm that I'll talk about in just one sec. But this is the only change to the negotiate. Then there's chained compression, which compresses multiple segments within each message. And so each message can have potentially different supported algorithms in the chain, and this flag indicates that such a chain is present. So you'll see the details on that in a second. Then finally, there's the chained transform that comprises a compression payload header. That is the same header that you've seen before, but I highlighted the original payload size as becoming optional. And then second, there's a new structure, the SMB compression pattern payload V1, that forms the body of the compressed data. It is inserted in place of the data, but it appears in the header. So I'll give you a schematic diagram. So here's the pattern V1 compression. It is a run length pattern matching, meaning that a sequential equivalent string of values which repeat for a specified count are basically recognized. The sender scans the message to be sent and looks for a string of equivalent values. It can match anywhere within a block. Typically, the way Windows works today, it looks at the front of the block and the back of the block. And there are a couple good reasons for that, just to cut down on the work that has to be done. But it scans forward, and if it finds something, then it additionally scans backward. If it doesn't find anything scanning forward, it does not scan backward. That's kind of a detail. The protocol supports it to be anywhere within the block, but Windows has some specific behaviors. The pattern V1 is valid only with a chained compression sequence. It is not a sort of a top level, first level algorithm. It's used only in a chain. It lives in a new structure and is flagged by the chained flag. Now that said, it can share the chain with other traditional compressions, and I'll show you some of the details of that. So just think run length, pattern matching. Well, equivalent byte pattern matching. Excuse me. So here's an example to help ground it. A chain compression example. I'm going to use an SMB2 write with 4K of data. And the data is going to have a very specific pattern. It's going to begin with a block of zeros. It's going to end with a block of FFFF. And it's going to have some recognizable pattern in the center. I don't really care how much of the chain looks like this. I just want to point out that it has pattern matching and compressible behaviors in the same chunk, the same block. So it'll be recognized by the sender as three compressible segments. The initial segment is a pattern V1 because it's a string of equivalent bytes, all 0. The final one is also a pattern V1, and the middle is viewed as compressible. All right, so this is a not atypical sort of pattern, certainly one which will help demonstrate how this works. You can imagine the pattern as simply missing some of these other things, the whole block zeros. So here's what it looks like in the top blue box. It's an SMB2 write with a bunch of header information, right? And following that, there's a buffer, a 4 kilobyte buffer of data that contains that pattern that I mentioned. This is going to be basically completely cut up, turned around backwards, and put back together as a chained compression message. It's going to begin, because it found 3 algorithms for the body, it's going to begin with an SMB2 compression transform header with the chained bit set. It's then going to have 3 compression payloads. The first is going to be a pattern V1 payload that's there in the number 1. There is much too much data to type this out, to write this all out on a single screen, so I did it with blocks. That's okay. So block number 1 has a pattern V1 for some length, or whatever the length of the zeros was, and a pattern payload of 0. I didn't go into much detail on it, but if you look at the pattern payload, you'll see that it contains a pattern here. That's going to be 0. And then a repetition count. So that's basically going to be 0, and that's going to be lin1 in our example. Second block is the, and that collapses to a very trivial 8-byte structure. The second block is going to be that LZ77 eligible block, that compressible block. That's going to be a compression payload header with LZ77 as the algorithm, or in fact none, any other algorithm is fine here. And it's going to contain LZ77 compressed data here in the 5 block. Then finally, there's going to be 2 blocks, 2 little chunks added, one for the compression payload V1 for the pattern V2 FFFF, len2, and finally a pattern payload for FF, right? So we've basically taken that entire 4K block and turned it into whatever the size of 1 through 7 is. We've prepended it with a transform header and stuck it on the front, right? Then the SMB2 write, which was not eligible for compression, is simply placed on the end. When this is decompressed, blocks 2 through 7 are reinflated to be the 4K, and it appears after the block, just as it would if it were sent. So basically, the whole packet is pretty heavily rearranged in a fairly compact way. So pattern V1 is eligible for any payload, but the most interesting payload for pattern V1 are virtual disks and VMLive migration. Recall that a virtual disk is just a file, but it's a very well-behaved file. It has very specific patterns in it. And VMLive migration, Hyper-V Live Migration operates over SMB in Windows. And so VMLive migration is in some ways similar in the sense that it is raw pages from the memory space of a user's virtual machine. There are a lot of pages of zeros in there, and a whole lot of them in some cases. And so they can migrate very, very, very efficiently if we can recognize them. It is eligible, however, for any payload. It'll work on any disk, any file, etc. It uses front and back pattern scannings, but as we mentioned in our example, internal segments are also eligible. So those heuristics, if you will, have been developed because they match well to the observed payloads that we have for the Windows use cases. There are many other heuristics available. It could be, maybe length is incredibly precious. Maybe bandwidth is incredibly precious. And everything should be compressed. Maybe we should only compress things that compress well, that kind of thing. Those are more compute intensive, and they should be entered into with care. But any other policy could be used. The protocol does not require any of these policies to be done. And one other thing to note, in Windows, they're applied only on greater than or equal to 4 kilobyte segments. Basically, in SMB, we get a list of pages. It's called an MDL, a memory descriptor list. And that memory descriptor list, typically for the bulk data, is a list of pages. And we will inspect only that payload. We don't even bother to look at the header. It's not worth compressing the header. It's usually small. It's usually very irregular. So Windows immediately jumps forward and just peeks inside the payload of the message. And so it basically looks at one page or more. It's not a fixed 4K number. It's just what we happen to get in MDL. So we view this as a bulk data tool, something which compresses bulk data primarily. Warning, alignment. Taking a look at slide 20. So we go back 2 slides, and we look here at item 5, LZ77, compressed data. We see it sitting here in the middle of other structures, right? We've got payload headers, payload headers, payload headers, blah, blah, blah. Well, how big is that segment? The answer is, it could be anything. It could be whatever the compression algorithm returned. Could be 3 bytes, could be 367 bytes. We don't know. So the compression payload header that follows it, there in block number 6, could be unaligned. Beware. The protocol does not specify that it be aligned. This may have been an oversight. We discovered it kind of late in the process. There was no time to fix it. There was almost no reason to fix it. It's not a big impact in general. However, it's something for the implementer to be well aware of. We may or may not address it in a future protocol update. We would do this in a compatible way, obviously. And if we did it, we would expect that it would be negotiated and upward compatible, but that over time the unaligned would fall away. It is what it is. It's a protocol. Protocols are forever once they go out. So you'll see this behavior for some time, and you should just be aware of it. There are other examples of this type of misalignment, if you will, in the SMB protocol. So I hope it's not unfamiliar to people, but it's basically a warning for the implementer. Be careful. I also want to note that there may be uncompressed segments mixed with the compressed segments. If a segment is short, less than 64 bytes in Windows, or fails to compress at all, and the segment is in between 2 incompressible segments, i.e., it's not eligible for compression because of the first bullet, but additional compressible data follows it, we send it as none. We basically use that compression fee algorithm of none, 0, and send it as a totally uncompressed blob. So note, previous warning on alignment. It could be a smaller, a non multiple of 8 segment. And it will sit in the middle of the other 2. If you look at segment 5 and slide 20, you imagine that it might be none as well as LZ77. But I'll note that these lengths and limits, all these things are behaviors. They may differ among implementations. Windows may make one choice, another implementation may make another. The protocol really doesn't specify at this level. It's an implementation's choice, how these things get chunked up and how they're compressed. The other thing to note is there are multiple transforms. Encryption is also transform, right? That was our first transform that we introduced back in SMB3.0. And it's different from chaining, and it's different from compression, right? It's its own transform. Encryption is always applied, however, after compression, right? It makes no sense to encrypt before you compress because you won't be able to compress in all likelihood. So we always encrypt last. Therefore, when we compress and encrypt, the entire compressed transform is then wrapped in a regular transform header. And that was just previously defined by the protocol. I believe I had an example of this in the presentation last year, where we had mixes of compression and transform. But I just want to stress that that has not changed. That encryption still trumps all. It's still the last transform we apply. It's the outermost transform. Yes, this is complex. I think it's just the nature of the beast. There are many strange and wonderful patterns and algorithms, right? The patterns coming in and the algorithms to compress them as well as possible. Compression is a very mathematical and a very obscure area in some ways. And so there are many different variants of it and many different algorithms that we will want to apply. It's just critical to test, test, test. I guarantee that as you develop this, you will find issues. I guarantee it. So prove it. Let me tell you some stories. I want to tell two stories. One of them you probably imagined. The other one I hope is not too shocking, but is a lesson. So the first one is documenting compression. As we documented this, we struggled. The documentation team, the team that I run, struggled. It was very difficult. Getting the text right has been a real challenge. Additionally, we found issues in the manual and automated document testing review. We went through this document with a fine-tooth comb, and a number of issues were raised, and we found issues while we were fixing the issues that were raised. We have done a lot of work that's visible in the errata. I really urge you to look at the errata and look at a future updated document. I just have a little screenshot here of it, but I wanted to share at least briefly. Oops, I've lost my errata page. Well, I won't waste time going to look for it. It's this page though. Here, I can click it. The errata page is really quite an interesting. No, it's not working. Is really quite an interesting collection of raw fixes. It will occasionally contain a redlined diff, and I'm hopeful that I can get you one of these future updated documents, which will allow that redline diff to be a little clearer. When you look at the page at the errata right now, it's sort of like a diff. It's a very raw transformation of the old text to the new text. But there are some significant simplifications and some significant clarifications in this text. They match what I'm presenting here, and I hope you will reference that rather than the March published text. The other interesting thing to really convince you is this link, Mitigating Vulnerabilities Endpoint Network Stacks. And I'm going to say, please let this not be another WannaCry, hold my beer, Samba, Microsoft. Here's the page. Mitigating, it was published on May 4th, just a few weeks ago, by one of our product security assurance engineers. And what they did was, what they do in general is they fuzz our product. They analyze our product for security vulnerabilities, and they use a whole slew of tools to do it. You can read about their tools, and you can read about some of the things that they've done, but they do person-in-the-middle fuzzing. They do fuzzing of SMB. Well, guess what? They looked at, well, here's their tool. They looked at a crash. After they were fuzzing, they discovered that the server crashed. And it led them to the compression transform packet. The one that I just mentioned. And we talk about the algorithm ID and the flags and the length. Then they disassembled the Windows kernel code and Jeremy will be chuckling loudly at this point. Guess what? Buffer overflow. So this was obviously a big problem, and it's obviously fixed, but it is, shocking, embarrassing, etc. But it was shipped, and you may have read about that in the news not too long ago. Well, this is what led to its discovery. So, beware, bad guys fuzz too, and good guys fuzz, and everybody fuzzes. So we got burned by this, and I hope that other implementations will not see their way to a successful delivery. So that's why I say, please not hold my beer. We don't want to one-up one another on this. So I've noticed that the Q&A is flashing like crazy. I'm running a little bit low on time. I'm just going to take one moment to inspect the Q&A. Hopefully there will be, let me see, 2. Okay. Is the new compressions requested by default for new Windows clients? The answer is yes. The Windows client will request the new algorithm to probe whether it's used. Will the new compression algorithm be used by the client? That's something I'm going to talk about in just a second. It is not automatically emitted by the Windows client, largely due to the CPU implications of the same. We don't want to slow down traffic if we don't have to compress, but we're working on some ways to turn that on. And the second question from Aurelian, does pattern v1 stand for version 1? Yes, it does. It is suggestively named. It is just a very simple, very effective pattern. There may well be a pattern v2. There may well be other patterns. The patterns will tend to match the types of workloads that we believe SMB compression will benefit. So you will see them very selectively applied. It is not sort of a billboard of lots of random ideas, but there will be potentially others. See if I can get that to go away in advance. Okay, protocol futures. Let me talk briefly about these futures. Possible protocol futures. I'm going to start with the word possible. And I'm going to say, yes, you've seen some of these before, but I'm going to mention them again because they are still in the pipeline. They take a long time. There are only so many vehicles by which they can be shipped, and things will emerge. Things continue to emerge. So this is a watch this space, but to remind you that they are still there. So the first one, matching with our client compression, is using compression. Currently, there's no way to force compression from a Windows system. The client negotiates it actively, but applies the rules locally. It does it by, the typical workload pattern is to not compress, and to basically compress only when doing certain understood workloads, things that the kernel initiates, for instance, and you can say, this is a compressible workload because it's Hyper-V, for instance. The server, likewise, only compresses when asked. Our server inspects the compression coming from the client. There was the request compress, therefore I will attempt to request to compress the reply. But if the client isn't compressing, then the server is generally not compressing either. We're investigating possibly surfacing compression as a robocopy option. So basically, robocopy / some new field, some new character will aggressively compress SMB traffic. Robocopy is already highly SMB3 aligned, so this will be a very simple change. But robocopy will be able to be used to exercise compression and hopefully to benefit from compression when the user requests it. Other client local mechanisms, this is obviously being turned on by some local signaling. Well, FS controls and handle options and this types of things are certainly in scope here, something to think about. Certainly something for another OS, such as Linux, Samba's client, to think about. Details and plans are still TBD. We're not making a promise here. I'm just simply saying this is being done. Quick is still on the roadmap. It's a UDP-based secure stream transport. This is just basic background. But in particular, it supports multiple streams with something called an application layer, port name or program name, connection migration, congestion control, lots of benefits, all very beneficial to SMB. Quick has been demonstrated for SMB down here in this link at the Storage Developer Conference. It basically can operate over Quick, and we intend to do so in the future. We believe that it has a big benefit for cloud-based SMB. So TCP 445 is commonly blocked. This will allow ubiquitous SMB access. Many other Quick scenarios. I just want to point out that this is still on the roadmap, and you may still expect it to arrive in the future. Signing, we talked about this several years ago. SMB3 still uses CMAC for signing. We have a GCM, a GMAC, AES GMAC encryption technique, which is far faster than even CCM-based signing. Encryption is faster than signing. That's what we're seeing. And most modern processors have a big speed up. Can we use GMAC to improve this? Yes. Back in SDCC 2015, 5 years ago almost, we talked about it, and we showed that it went up 46%. CPU utilization went down 46%. It's gotten better since then. So the CPUs have gotten better since then. So this is still on the roadmap and still expected. It's a very simple change. There will be a new negotiate context, which will look for an algorithm, an alternative algorithm to CMAC. If both client and server support it, it can be used. Signing and encryption in RDMA. Currently, RDMA is not encrypted nor signed. The reason being that the payload is transferred via RDMA, which is not part of the SMB protocol. And so there's a big penalty, if you will, in that loss of protection when you go to RDMA. We talked about this before. I believe we talked about this in that 2018 presentation. There's a big performance gain by which you can pre-encrypt, basically bounce buffer, the RDMA data on both sides of the wire and complete the request. There's a slight protocol change to do this. Normally, the previous slide would require no protocol change, but we have a nonce. We have an expected signature and a nonce. So that requires decoration in the payload, and our solution may well be to use the channel. We already have a channel for RDMA. You can simply add more data to it to exchange that information. And finally, near and dear to my heart, push mode to persistent memory in DACs. This slide has been seen many times before, but I just want to point out the last item in the bullets on the left. Minimal SMB3 and RDMA protocol extensions are required. Unfortunately, the RDMA protocol extensions are absolutely required. So this has been delayed, and its benefit has been measured in the meantime. But in 1 second, I'll give you the good news. The benefit we mentioned back in last year's. Oh dear, I have the wrong link at the bottom of my slide. I will have to fix it later. At SDCC 2019, back in September, Matthew George and I made a presentation in which we took a prototype push mode implementation on Windows and displayed it. I've cherry-picked the best numbers from it here. Basically, you'll notice here SMB is performing 4K writes in approximately 80 microseconds. And we can improve that to approximately 15 microseconds by using push mode RDMA best case. We get a similar benefit for reads where the server performs an RDMA write. We save 30 microseconds in the base case and we achieve the same speed in the first case. The really, really, really important thing here is down on the left. CPU utilization on the server is 0 in both cases. The CPU on the server is doing absolutely nothing in these things, which is where most of this benefit comes from. So here's the good news. The RDMA protocol extensions are, in fact, advancing in both IBTA and IETF. I'll show you the detail in just 1 second. There are 2 primary extensions in the RDMA space. The RDMA flush is the basic flush to durability. That's the minimum requirement. There are two additional operations. One is present in both, one is present in one. Atomic write is a sort of a transactional write. It's perfect for a log pointer. You write the data, you make the data safe, you drop the pointer. You write the data, you make the data safe, you drop the pointer. You go again and again and again. Atomic write supports that remotely without CPU on the server. And second, the iWork extension does the same thing, but also adds a verify to compute and allow to be verified. These two drafts published March 9th, and the IBTA one is currently in final review. I'm just going to skip forward to one final note, Interop events. We held the SDCC EMEA event in Tel Aviv back in January. Redmond Dev Days was supposed to happen in June. We deferred that, Microsoft, and we deferred that. We did this prior to any of the COVID-19 situation. We decided to merge it with the SDC 2020 SMB Plugfest. We did this because we discovered that it's really difficult for people to do two events, June and September. The SMB portion of Dev Days was intentionally merged with a larger, improved SMB3 Plugfest. Unfortunately, SDC 2020 at Santa Clara is on the bubble. It has not been canceled. It's, in my opinion, very, very unlikely to occur as an on-site event. It may occur as an online event like this one is, but it's very unlikely to happen. It's very unlikely that we will have the authorization or that anybody will have the ability to perform an on-site event. So I'm going to just exhort everyone to please, please, please keep testing. The Microsoft test suites are usable anywhere. You can download VHDs, you can run the tests, whatever. Microsoft is committed to future events, and it's possible that that will include remote interop testing. I don't know. But keep testing. It's so important. It's been the hallmark of SMB's industry success. All the vendors interoperate. And I just want to say we continue to evolve the protocol steadily. We incredibly value the Samba contribution and Samba partnership. Let's keep our momentum despite the impact that COVID-19 is imposing.